Alrighty, let's try streaming. Alright, so I have my audio going, and I also have my video camera going. I also have dual monitors, so my poor little laptop is probably screaming right now. But we'll give it a try. We'll see if this works. Okay, first things first, I should have set this up in advance, but gonna get people on my stream. Come on. I want to know what the stream quality is like. Alright, I'll put this over here. And let's get going. Launching up KiCad. Alright, I'll try not to do too much in the bottom right here. I'm going to need some gentle reminding about that. Okay, so this is part of the connection machine. Building essentially a breakout board for the Cypress Semiconductor CY8C4 yada 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 yada. What's nice about this chip is a Cortex M0, pretty full featured, but it is less than 50 cents in single unit quantities from places like DigiKey. So super accessible. And Cypress has some cool architectural things that they have in their chips. Their biggest selling point is like what do they call it? PSOC. So there's a lot of like software defined hardware peripherals inside like Cypress devices. So that's kind of cool. But I just got it because it was cheap. And the idea is I already purchased some. So I got a roll of 200 of these things, and because they have I2C on them, I wanted to fill up an entire I2C bus with these microcontrollers and essentially create a huge network of distributed MCUs. And I'm working with a friend and some other cluster fighter. Fellow cluster fighter that we're going to try to build some system that can let these things essentially operate as a single unit. So I think, let me try to remember where I was last. So I have a big old bag of 7-segment displays, through-hole 7-segment displays that I got from, it was a closeout sale for, some supply, like electronics supplier, that had a bunch of surplus parts and those kinds of things. It was called HSC Electronics here in the Bay Area, also known as Halted. But what was cool about it is during the blowout sale, everything was super cheap. Go figure. And I picked up a whole bunch of these guys, pretty standard, run-of-the-mill, through-hole 7-segment displays. And I was thinking that for each microcontroller that is on this board, there could be a 7 segment display. So basically, you could get, kind of information about what was happening at the individual processor level, um, based on what was going on the 7 segment. So that's the idea anyway. I didn't want to build a full footprint for it for the electronic side, um, just because I guess I could. Ugh. Building electronics footprints is a laborious process and kind of a pain. I prefer to just do layout and stuff right now, but I don't know. For now, let's focus on fleshing this out. Yeah, so what I was going to do here is essentially like just plop down a 14 pin connector and then whatever, wire it up by hand basically, just kind of jumper the things in there. Because I think I had a let's see, I had a data sheet in here for the this one in particular is a DL7760R, which doesn't turn up a whole bunch of stuff. This is micro semi. Was this a little teeny tiny server? So it's the 7760 is sort of like the jelly bean part number for it, but also the apparently name for a printer. 7760, 5082 by On Semiconductor. Okay, getting closer. And Fairchild, now owned by On. I just find it so interesting. Like, I don't know. It's sort of like, I guess the industry is mature enough, but you get to a certain point and it's like, all right, you just need to start swallowing up, other corporate entities. Let's see. So what I'm looking for, I have my particular variant. Yeah, these are all evenly spaced. The footprint on this thing is kind of weird. If you look at it, I don't know if it's visible on the camera, but it's, quote, 14 pins, but there's a bunch of, like, non-populated pins in there. So it's a 14-pin package, but there's 4, and then 5 is 9, 11 total pins. So maybe this will work. It's a 16-pin package, though. No, that's 14. So, yeah. No pins. 7760. Okay, I guess in this case, it's a type C. Based on this. Oops. Keep forgetting. I don't like keeping things on my right side, so I will probably do this. Come on. What you doing there? There. Okay. Cool. Uh-oh. Scaled the window. No, I want it to be canvas. Ah! Everything is breaking. As you can clearly see, I'm new to streaming, and I'm not yet very good at it. Things are still kind of breaking here. Uh, there we go. Okay, cool. I'm using OBS Studio, which is really cool. It's a super nice, I think it's open source, but it's a freeware streaming tool for all the platforms. I'm currently using Linux. I run Arch, by the way. And it's a never-ending series of debugging issues. So, okay, we have established here that I have version C, and I have one of these, unused decimal position. So they have 2 decimals, but only one of them works per package. I have part C. And I think I labeled this correctly. Yeah, A, anode A, F, common cathode, no pin, no connection. I think in my case I have, okay, no connection. So I do have a pin there. So it would be no connection, and then pin 7 is anode E, anode D, anode decimal place, anode C, anode G, no pin, anode B, and common cathode again. Cool. Okay. Yeah, that is perfect. That's exactly what I want. So I made this pinout with a datasheet from a different company. So that's just the joy and pleasure of jelly bean parts. And jelly bean parts meaning like a bunch of different manufacturers make the exact same thing. And yeah, they can oftentimes be, swapped in. They're sort of like pin for pin and feature for feature compatible sometimes. And a big old asterisk there. All right, so now the next trick is going to be we need to wire this up. So this is just a standard header, standard 100 mil pitch. So we'll whatever, not worry about that right now. And then I'm going to copy this block, put this over here, copy this block, put it over here. So here is, probably going to order these. Find that, so by the way, this is this is exactly this same sort of stuff that I do in my day job. I'm an electrical engineer by trade, and I build boards for business and for pleasure. A, B, C, D, E. And one of the things that I've learned, so where I work, I do mostly it's essentially electronics consulting, and we have a whole bunch of different types of projects that come in the door. The company started off mostly doing robotics, but we do lots of consumer electronics type stuff. But one thing that I found doing PCB layout and schematic capture for the same board is that that's a fairly uncommon way of doing things. That a lot of the time you have people that will just do schematic capture and then throw it over the wall and give it to someone else so that they can do the actual like physical board layout. But the projects that we do, I guess, are small enough and self-contained enough that we have kind of, as electrical engineers on it, full scope over the whole schematic capture and layout, and this feedback cycle between, doing layout, then building footprints for components and stuff, and laying things out on the printed circuit board, and like discovering errors and bugs and sort of smoothing through that whole process. Find that it's a lot faster. So that's kind of novel, apparently. But okay, so here we are. Got these things. You saw me lining this up over here. I only have 16 pins on this part, and these LEDs take up a big old chunk. So what I would like to do, so the architecture for this, and this is just kind of like a first run prototype, the architecture for this particular board is going to be to have probably, I don't know, a nice round number, like 100 of these things connected together through I2C. And I2C protocol, it accommodates 127 devices because you get a 7-bit address. And it's like 7-bit address, and then 1 bit for are you reading or are you writing. And that is what I'm going to consider the global connection network. So every node can talk to every other node. But if you have full interconnects between every single node, you run into certain constraints, certain limitations, and those are going to be for max speed. So in the case of I2C, it really at its max, as per the specification anyway, it maxes out at like 400 kilohertz, and then depending on like the load capacitance of your particular board, and the value of the pull-up resistors that you use and stuff, that will all have different effects on like the total speed, or total practical speed. So what I also want to do is implement on some of these other GPIOs, because they have there's timers inside the chip, and you can have basically you can time pulses coming in as inputs, and you can do pulse width modulation on the output. And what I would like to have is essentially like a high-speed communication from node to node, so like nearest neighbor. You can talk really fast, but if you ideally it would be something that you can buffer messages from one node to another, and as you buffer them, you're going to encounter delays as the message kind of gets read and analyzed and moved through the chip. So you can send messages between neighbors very, very quickly, but at a certain point, if you have to travel if messages have to travel more than 4 nodes or 5 nodes or 10 nodes or something like that, it makes more sense to use the global interconnect network. And basically this is a global interconnect network being I2C addressing. And what this is meant to do is sort of serve as a test bench for learning routing protocols and stuff, and it's figuring out different topologies and sending messages back and forth between a whole bunch of interconnected devices. So this is all kind of related to cluster fighting and that fun stuff, which if you have not seen cluster fights, I'm gonna pull this up real quick. Gonna pitch my brand. Cluster fights. If you go to clusterfights.com, currently don't have a fight on the books, but holy shit, look at that. Melt your face off. Computational excitement. So we have we have a chat and we have a mailing list. So our chat we do on Matrix, the Matrix network, which is the what do you call it? So it's kind of like IRC, but a little newer. Does some cool stuff, supports emojis, that sort of thing. Very important. And yeah, so that's sort of like the place where we go. We all hang out. We swap, topics on clusters and how they work and what would be cool and how to implement them and all that sort of stuff. So you can see all this stuff here, and I'm actually going to post to one of my other chats. All right, but yeah, this is just kind of our hangout, and this is where we, swap cool ideas and discuss cluster fighting. So cluster fights is essentially a group of people who build supercomputers and distributed systems, and computing clusters and fight them against each other. So we have a competition that we do about once a month or so. Haven't had one in a couple of months. People have kind of been taking a short hiatus from it, but it's a group of really smart people and building cool things. So it's all about building some rad hardware and having them do cool stuff. So check it out. Go to clusterfights.com, join our mailing list, and check us out on Matrix. All right, so that's the pitch for now. Let's get back to the board. All right. Cool. All right. So because we have a whole bunch of GPIO that need to be driven, we also have a limited number of GPIO pins available. And on top of that, I should probably pull up the data sheet for this thing. A lot of the time, so this microcontroller can run off of 3.3 volts or 1.8 volts. So it's designed to be variable like that. And what's kind of cool, right? So these bottom three pins, P30, 31, and 32, they have a different internal power supply. So they're connected internally to VDD-IO, while all of the port 0 and port 1 pins over here, these guys, those guys are connected to whatever the VDD pin is. And that means what you could potentially do, they provide the example of saying that VDD-IO could be 1.8 volts or basically less than your VDD. I need to check the datasheet to see if this thing can do 5 volts. So that would allow you to pull this up to 5 volts and essentially have 5 volt input logic and be 5 volt tolerant, so you didn't have to put level shifters and all that extra jazz on there. But I digress. So because we have all these GPIO, we don't know if these GPIO pins can source or sink enough current, generally at least 20 milliamps for red LEDs. We don't know if it can source or sink that current. Probably can, but it'd be nice if we didn't have to. Or rather, it would be nice if we just could use less pins. the point of all this is I want to put a shift register on here. And the shift register is essentially going to be a clock and a data line. So I use two GPIOs in my microcontroller, and then I'm able to shift in serially, one at a time, the bits that I want to light up. And if it happens fast enough, it is imperceptible to the viewer, and will allow me to have some extra wires for, my high-speed node-to-node networking, and also let me have my display. So have my cake and eat it too. Okay, cool. Let's do this. This is the CY8. C4013, blah, 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 blah. Lots of digging into data sheets here. Just want to have that in my back pocket. And then let's go to DigiKey. Oop, already here. And I'll look up shift registers. Okay. Let's see. I want cut tape. I want in stock. I want active. Wish there was a way to set it so that every time I went to DigiKey, it would always populate those fields. Number of elements and bits per element. I've got 1, 2, 3, 5, 6, 7, 8. So 8. Actually, we'll clear it. Oh, good. So a lot of these things are single element 8 bits wide. And so looking here, output type, complementary, tri-state. So this means there's like, I guess, 2 outputs, and one goes high and one goes low at the same time, and vice versa. Tri-state means you can connect a whole bunch of the inputs together, and then push-pull means it can be driven high or driven low. Okay, so we have these guys, and then what I want to do is, because I really don't feel like making any more footprints than I have to, I'm going to check the KiCad libraries and see if we can't get some sort of shift register in here. Right. Cool. So now we're just doing some cross-referencing. I could look at cheapest or could look at most available. I'll look at cheapest, I suppose. 36 cents and something that's easy to hand solder. Yeah, the T-SOP, so this is what, 4 millimeters wide. That's 4.4 and 3.9. Not really a huge deal either way. This is a 165. Okay, so a lot of these things are kind of like jelly bean footprints. At least that's how KiCad treats them. KiCad, whichever, or dip Dip, 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 dip. No, I don't want dip. Ugh. I really don't like surface mount, or sorry, through-hole soldering. Once I have crossed into the realm of surface mount, I never want to go back. '74 HC 165. Okay, well, I guess we can do this. We have a relatively satisfactory symbol. We want a excuse me. Package. Oh goodness, come on. This is a TSSOP or a SOIC. Either one. SOTSOP. The top one is a TSOP. Alright, well, blah. TSOP 16. So what I want to do is I'm going to pull up the data sheet for this guy over here and see if he matches. Cross my fingers. SOP 16. Ooh. Yeah, so even though it's so SOP is small outline package, and 16 pins, and then P, that's for pitch, so that's the spacing between the different pads there, and I want to make sure that I get the pitch and pin spacing right. That's a QFN, quad flat, no lead. This is the TSOP 16. Pitch is 0.65. TSOP 16, 0.65, and there is on this guy no exposed pad. Cool. Well, awesome. Hooray for standardized footprints. Okay, cool. We'll plop it on there. Boop. Excellent. Alrighty. So, cats. Cathode. That is the part that's going to go to the negative side. Guys, we'll go to what does DS mean? Is that common in these things? Yeah. Oh, okay. serial data input. Well, there you go. So I'm going to do... Okay. Cool. So this particular one that I found, MC, I don't know what MC is. Outputs directly to these things. Operating voltage 2 to 6 volts. Works for me. Alright. Copy that. Put this here. Come on, you. Alright, and then what we will do is plop a bypass cap on there. And as you can see, I have not named these yet, annotated them rather, nor have I chosen values for them. So I'll probably do that at I'll have to do that at a later stage. Okay. God, ain't she a beaut? Look at that little hat. So cute. Yeah, I find that half of my time is just moving things around to make them look pretty. That's the thing, right? Like you have, come on. You got a schematic, and the schematic is, you know, it's important to have a correct schematic to inform the layout tool, kind of like what parts go where and what things are connected and all that sort of stuff. So you get your, like, you know, your net list correct. However, it is also important to make it nice and human readable. Because if it's not human readable, then what the heck, man? Like, what's the point? You know, it's like writing code, I guess. You know, you want to make sure that your code's maintainable. You want to make sure your schematics are maintainable. So you got to make sure they're aesthetically pleasing to some degree. Or maybe it's a philosophical discussion. Who knows? But I like making them look pretty. Makes them easier on the eyes, easier to read. So pin 1, that's a serial shift parallel load. I want to serial data input, parallel data inputs. Wait a minute. Aw. Did I screw up? I might have chosen the wrong thing. I want these to be parallel outputs, not inputs. Boo. Serial data outputs. Serial data inputs. Yeah. Okay, well, that sucks. This is not the droid I'm looking for. I want to do shifting in, yeah, function. There we go. Wow, sure would pay to check out the other filters here. Oof. Yeah, I guess we want serial to parallel. We do not want the other way around. Parallel or serial to serial. We want it to be parallel. This is, ooh, okay, close. This is a 165. This is in fact a 164. Wow. I have a cat named MOSFET, and he just ran out of my closet. He's a little black cat. It's very cute. Okay, well, we can do this. Oops. So I find that one of the things that makes me most productive when I'm doing PCB layout is PCB layout and schematic capture is figuring out the hotkeys, the keyboard hotkeys. It's like the people that like learn how to use Vim and they're like suddenly unstoppable, you know, programmers. But it's like, yeah, especially switching between a whole bunch of different ECAD tools like Altium or KiCad. You know, they all kind of blur together eventually. But, oh my gosh, regulator switching, no, it seems like 164 is a much more, yeah, this is the one. And look at that, comes in TSOP packages as well. I love it. 74 HC 164. And this is a 14 TSOP, 4.4 millimeter width, 4.4 millimeters by 5 millimeters. Cool. That is the one. Ah. Yeet that one all out of here. Let's see. So, okay. Pet peeve. Here I am trying to make these, attach the, you know, these guys here. I want to attach them over here. So to do so, I want to, like, you know, rotate them, right? So what is obnoxious is, so to do that, to make him go from right to left, you press Y, okay? As if you were rotating them over the Y-axis. But in Altium, if you want to do that, the key is X, as if you are only operating on the X-axis, moving from left to right. So it's these, it's like accomplishing the same thing, but with a mirrored convention, and it's inconsistent, and I screw it up all the time. So, well, you know what really grinds my gears? Yeah, when your CAD tools aren't consistent across vendors. That's what really grinds my gears. Okay. Actually. Oh, all right. Now, MR, what does that stand for? Output type push pull. That's fine. That's fine. Ah, goodness. I've got, okay, notice plus 3v3 and plus 3.3 volts. KiCad does this really obnoxious thing where, like, if you want a power symbol that is different from the ones that they have in their libraries, you can't just rename it. You have to create a whole new part, essentially. It's very troublesome when you're trying to, like, you know, you've got a couple of different, like, you know, I don't know, you have like multiple like 3.3 volt rails, for instance, and you want to be able to, like, you know, differentiate them. I don't want to create a new part for that. I just want to rename that to 3v3 underscore something, but you cannot do such things. See, power symbol value field cannot be changed. Dumb. Okay, so what we're gonna do then, just to kind of get by here, delete. Do I want to delete that? Nah, I'll leave them be. It's gonna get me eventually, but that's okay. So the reason I did this is I'm making a lot of shortcuts and assumptions, and, like, this is meant to be a prototyping PCB. There we go. So this is connected to 3.3 volts. This is connected to 3v3. This is so that 3.3 volts is 3.3 volts. All right, plus 3.3 volts. That's powering the microcontroller. All right, but this is only 150 milliamp LDO. I don't feel like putting a switcher on there. I guess 250 milliamps. But this other one is identical. They're the same value, same, you know, I'm gonna have the same capacitors on them and everything. But the one for LED and one for system. This is system, this is LEDs. There you go. Voila. And it just helps me not overload them. So cat, delete, delete the cats. I don't need any transistors. Connect to ground. Connect to ground. Cool. Now we can connect these guys. So 74, that's the 165 still. This is the 164 now. Okay. Same in every way, because it's from the same series. Alright, CP. We'll call this shift clock. Serial data inputs. Interesting. A1 and A2, DSA and DSB. Oh, how interesting. So this is our, what MR I guess is. Master reset. And what's important to note about that is it is active low. Okay. Shift clock, shift reset. Clock reset, serial. data inputs. So D is data input. So this means if your clock is rising, okay, so let's do a little truth table analysis, function analysis here. So this little squiggle, this is on falling edge of clock. So if reset, if it has a low value, do nothing. Everything is going to be low. So when you hit reset, it's just going to pull everything down. All right. So you're at a reset. Reset is driven high. All right. If you have a falling edge, nothing happens. Nothing happens on a falling edge. Who cares? All right. So the X is don't care. All right. Now we have a rising edge. And it looks like, so if we have a rising edge, clock is high, A1 is high, and D is data, then it's going to have data. Well, they're identical. So what happens if, what is the point of this? Why do you have an ANDed input? Huh. Might be useful for something. But I guess for now, let's just go ahead and no, you know what? Rather than connect it to that, let's have some fun. So either of these things can be data. We just need to make sure that, you know, there's at least a high one. So, yeah, okay, cool. Let's do this. Go ahead and do this thing. Because we can spare 4 pins, this is half the pins from the things that we needed to drive. And it only costs us software development time. Yay! So I don't want them to be clocks, but I do want them to be data. Data serial A and data serial B. Cool. Yeah, well, whatever, man. Just gonna go ahead and I'm just gonna let those things do their thing. So the whole idea is that I want to get this thing out the door tomorrow. Why? Because I am currently trying to speed up the way that I design PCBs. And the way that I design PCBs is slow and meticulous, and slow and meticulous is not a very Silicon Valley way of doing things, so I need to move faster and break things. Oops. Okay, and then these guys, in order to practice the interconnects and figure out how they are going to be connected and so on, I am comfortable with just, what? I'm gonna get you on out of here. Come So these guys here, the things that I just put on there, those are net labels, and the net labels are slightly different from global labels. KiCad and these other guys, they have this concept of schematic hierarchy. So everything is just on one sheet right now. But I guess you can think of it as like local or global variables if you're a programming type. So the net labels, those are local to the schematic only. However, these guys here are global labels, and then those would apply across the entire set of schematics. And then they also have, look over here, they also have this concept, so global labels, and then they have this concept of hierarchical labels, and Altium refers to these things as ports. So it's a way that you can essentially take a signal and migrate it to the schematic item, like the parent schematic item in the hierarchy. And it allows you to sort of like have a super complicated schematic, but if everything is self-contained and you only have like 2 inputs and 2 outputs on the hierarchy above, you have a sheet symbol that is represented just as 2 inputs and 2 outputs, and sort of the complexity of the schematic sheet is, you know, abstracted away in a little sheet symbol. So, you know, there's pros and cons to doing that. You know, some people like really flat global labels for everything. Other people like the hierarchies and all that sort of stuff. It's a topic of debate at our office. So make sure that's lined up. And then all I'm going to do here is, because I have, oops, boop, 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 I want that there. Because I have some spare Pinarinos. Come on now. There you go. All these guys are just going to go to actually, I'll delete that. Actually, no. I won't. Yes, I will. Nice little bundle. Yeah, so that's kind of interesting about this chip is that its main serial interface, it's only officially like only official serial interface that's like built into hardware is I2C, but it also has the serial wire debug hardware, so that's like for programming and debugging ARM processors. It's essentially like 2-wire JTAG, and they have them on the same pins. But what's also super cool is that there's an I2C bootloader that it exists for these things. Sorry, my roommate is also a Twitch streamer. She is more popular than I am because she doesn't do she doesn't do PCB design on her streams. But what was I saying? I forget. Something about I2C. I don't know. It's been a long day. I'm rambling. Oh yeah, serial wire debug on the I2C pins. There's also an I2C bootloader for these guys. So the idea is, because these things are all going to be sort of connected in a big global I2C network, it's going to be rad as hell to be able to have a single firmware update and essentially propagate it across this this entire like network. So like you program one, and then this one goes and programs another, and that one goes and programs another, and so on and so forth. And you essentially have them be self propagating changes, firmware updates anyway. So that's the idea for this. Eventually, we can dream. So let's see. This is 1, 2, 3, 4, 5, and 6 spare pins. So let's go ahead and just add a connector. Connector 1 by 6, and we shall make it male. It's a boys' dance party. Pin header, and I want 2.54 millimeters vertical. Pin header. Oh yeah. My friend Dan said that the stream looked good. Exciting. So Dan is the other cluster fighter that I'm working on this stuff with. He's whether he knows it or not, he's going to help me write the software for this thing, because I'm not a very good software guy. But what's kind of cool is we've been talking about in the Riot channel, we've been talking about cellular automata programming. And if you've ever played like Conway's Game of Life or anything like that, there's a way of essentially programming, solving programming problems by using cellular automata, and this is a piece of hardware that is very well suited to that method. So that's pretty cool. So gotta make sure it's pretty. It's the most important part. Boop. Oh no, that's not pretty. Boop. These little signals are all boxed in there. So I'm probably going to take a break once I would say that that's about all the stuff that I want on there right now, because it's mostly just connectors for power. These are jumpers, input power, voltage regulators. I think this is all I need, so I don't need an oscillator on this thing because it has an internal one. Heck yeah. So, quick side note, the reason why these particular chips are so friggin' cheap is because they are meant to be, like commodity things. So, this particular chip, it has, these things called current DACs or IDACs, digital to analog converters, and it lets you use those, or encourages you to use those as a capacitive touch sensing system. So these guys are meant to be like the little microcontrollers that you have powering your ovens or your kitchen ranges and stuff, or like your mouse pad or something like that. So that's kind of cool. It's a lot of the times like you've probably used these chips before, since they've been in existence for a couple years now, probably since like what it was 2014 or 2017, something like that, when this particular chip came out. So you probably have these chips in your home already. So let's see. Just want to verify that I don't need an oscillator. SCILO, internal low speed oscillator. External crystal oscillator. The clock system consists of the internal main oscillator, and an internal low frequency oscillator. So there's two of them. So if I want a better oscillator, I'm more than welcome to attach one. The IMO default frequency is 24 megahertz, and it can be adjusted from 24 to 48 megahertz in steps of 4 megahertz. Hey, would you look at that? Huh, okay, cool, awesome. Well, works for me. Oh, is there a reset? There should be a reset on here. External reset. Oh no! An internal power on reset is great. Okay, so well, the the data sheet is telling me that for this particular 6-pin package, if you want to reset it, you just got to turn it off and on again. Go figure. So it's got some internal logic. So like basically, like, you know, if you're unplugging the power and plugging it back in again, it goes through this like they call it POR, or power on reset, and you know that goes and sets all the registers to their, you know, their default values and all that kind of stuff. So let's see. I'm gonna see. Apparently, there's a chat for Twitch or something, and I don't know how any of this works. Activity. Just gonna check out my dashboard. Haha. Glad I checked. Nobody's watching. That's okay. Oh, I got 4 viewers. Never mind. Yay. 4 whole people. That's the most people I've ever had watching my stream. Nice. I don't know how to chat with you guys. Is that how to chat? Nice. Confirmed KiCad. Is it KiCad or is it KiCad? Slack McGee. Or, if you're feeling very fancy, is it KiCad? Alright. So here's what I want to do. You see these guys. They're asking me the question. You and J. So in order to have them stop asking stupid questions, I will annotate this schematic. Keep the existing ones. That's only if they already have numbers, if I've already gone through this process. But I haven't, so there we go. Boom. All right. Everything has a number, and everything is amazing. Okay, so I think every single pin on here, except for the power, well, no, power indeed. I think just for the sake of it, I'm going to do this. I'm going to add a 4-pin connector, and then that's going to have each of the power rails and ground on it, and then, well, actually, so there's this, that's the little jumper thing. Ah, confirmed. KiCad. Yeah. I heard once somewhere that it's like, oh yeah, it's the supposed to be like KiCad, like a key, but then like they actually had like one of the developers who you know uh, whatever came up with the thing with the software originally, and he's like, yeah, I don't really care. It's one way or the other. It doesn't matter. So have a holy war. So I don't know. I kind of just say both. But I think this is more or less ready to go to the mapping netlist to or mapping the symbols to the footprints. Definitely doesn't matter at all. Some people think it is very important, and those people don't matter at all. Okay, cool. Let's see here. At this stage, Yippee-ki-cad, motherfucker. So, the set of people that are neurotic and the set of people that live stream PCB design, I would imagine have significant overlap. So one thing to keep in mind. But okay, cool. Yeah. Let's see. Create, delete, and edit symbols. Let's go ahead and push this to do a DRC. I'm gonna ignore pretty much everything that shows up here. Yeah, who gives a shit? I don't. Okay. So right now, what we're doing is matching up all of these. Sorry, Daniel Robert Lewis. I do not have any lo-fi beats in this stream. I didn't have audio in my first stream, so this is a significant improvement. So just bear with me. All right, we'll get there. We'll get the lo-fi beats. So I don't have any values for these things. What I am gonna do is I'm gonna say, okay, I want 0805s. Just a whole bunch of 0805s because they big. Hand slaughter. So, okay, quick side note here. There's been a lot of discussion at my office about capacitors and bypassing. Let's see, so Kemet. So you think, oh, capacitor. A capacitor is a capacitor is a capacitor. You put a whole bunch of them. The more you put on there, like a capacitor. This is eye-opening. So this is you think that like, okay, it's essentially a bucket of water, and you pick a value and you hope that that's enough of a bucket to store all of your electrons in, and away you go. Well, as it turns out, capacitors are really weird, and this goes like not just for Kemet capacitors. Kemet's a manufacturer of these things. This is their simulator tool, and they have a whole bunch of like empirical data that they got from this, from testing their different caps. And as you can see, like capacitors, this is looking at its impedance, and ESR, which is the equivalent series resistance of the capacitor across different frequencies. So like this thing here, this red line, this is the impedance. So essentially, as your frequency increases more and more and more and more, right around like, what is that, like 2.3 megahertz, something like that, that's your lowest impedance. But because like, if you remember from circuits, if you ever took that class, that like a capacitor, if you have an AC signal through it, the higher the frequency goes, the more and more it looks like a short circuit. So it's going to be like, oh, it's like, it's basically just a piece of wire instead of a capacitor at high frequencies. But at this point here, you reach this transition where it's like, why the heck does the impedance and like series resistance go up? Well, that's because the physical package of the capacitor itself, it has inductance in it, right? So this is like, a capacitor is actually a really complex network of capacitors, resistors, and inductors. If you look at the SPICE model here, so you have like all of these, like, this is essentially what is happening at your different frequencies, and you can see that even at frequencies, this network here of inductors in series and parallel, and resistors and capacitors in series and parallel, they all change with frequency as well. So it's a very, very like complex dynamic system in play. And when you have so that was just looking at a single capacitor, and generally speaking, what a lot of people like to do is, also this is pretty crazy. So if you look at capacitance versus your voltage bias, so you think like, okay, a 10 microfarad capacitor is going to be 10 microfarads no matter what you do with it, whether it's at you got 5 volts going into it or 3 volts going into it. That's not true, right? Look at this thing, right? So this is only a 10 microfarad capacitor when you don't have any voltage on it at all, and it immediately starts dropping off. So this thing is rated for, I think, 10 volts. But once you get to 10 volts, or maybe, no, this is a 25 volt, but yeah, like, it's a 25 volt cap, so it'll, detonate on you at 30 volts. But like, say you're putting 10 volts on this capacitor, like, you have a minus 75 reduction, minus 75% reduction in your capacitance here. So this thing is only a 1.5 microfarad capacitor if you have 10 volts going to it, which is like, that blew my mind the first time I realized that like a capacitor is voltage dependent and frequency dependent and like all this other stuff, and that is for a single capacitor. And when you start adding extra capacitors to it, it creates this very complex interrelationship between all these parts. So like, so I'll add another one. A lot of people, what they do is they'll add an 0805 10 microfarad capacitor, and then they'll be like, I can't find the one that I want, so I'll add an 0603 X5R, let's see, and then, you want to add, like, you add them in 1 decade apart, right? Put that in 0805 as well. So you do that, call this like 16 volts, 1 microfarad, decade apart, and you think like, oh, like, I got one thing for the, like, the big beefy transients, and another thing for like the high frequency transients. So as you can see, like, their impedances are different, and their ESR curves are different, and that's because they're, well, in this case they have the same package, but a lot of times it deals with the package size, but it's also the capacitance change as well. But look at this. So I'm going to combine these impedances. If I have these two capacitors here, boom, you suddenly have this weird like trough and then this crazy peak, right? So like, if you're expecting, to be operating right around here at like, 2.3 megahertz, it's like, cool, yeah, look at that. Your ESR is pretty low, and your reflections and electromagnetic interference and all that kind of stuff, like, that's low as you'd expect. But you added this extra capacitor on here to like help you buffer your, to bypass your circuit. But as soon as you start operating in like 3.5 megahertz, you've just gotten rid of all of that bypassing, and it goes, peaks up here. And that's with 2 different capacitors, 1 decade apart in the same package. And if you get a whole bunch of, like, you're not factoring in like capacitance of the board itself, and like, there's a whole bunch of other factors that come into play for this kind of thing. So not like it's going to matter at all for this particular PCB that I'm making. It was just one of those things where it's like, wow, like here I was thinking I had a understanding of a very simple circuit component, and then it's like, no, real life is much uglier. So I digress. Everything is going to have an 0805 package, and probably sometime after I've sent the boards off, I will determine reasonable values for them. They're probably just going to be like 0.1 and 2.2 microfarads or something like that. I don't know. I don't really care. So it's going to have pretty bad bypassing performance and bad ESR performance, but at least this doesn't have to go through FCC testing or anything like that. Ha. So what does Dan say? I've been doing circuits at plus or minus 12 volts recently. Never knew that it might have a different capacitance at my voltages. Yeah. Mind blowing, right? So I am just, yeah, always in awe of the new little things that, that apparently have been around forever, but I just learn about these things. 0805 hand solder. All right, and this 7-segment display, so what I want to do is I just want to find a connector. It's going to be a pin header, 2.54, and it's going to be vertical. Cool. All right, sweet. Look at that. All those things. Normally this takes a really long time to match these things up if you have like, thousands and thousands of components, but I'm going to apply. I'm going to save the schematics. So what's interesting is that in KiCad, KiCad, these particular like this matching, so you have a symbol, you have a footprint, and then you have a linking of a symbol to a footprint, and that is saved, that linking, in order to keep it like loosely coupled, I guess. That happens in the schematic layer, and then is carried over into the PCB layer. All right, so everything's annotated, everything's got connectors, everything's got footprints, everything's ready to go. We're going to generate this net list. So that says generate the list of all the footprints and all of the like pins and what they connect to and how they connect and all that kind of stuff. It's basically just a whole bunch of metadata that links the symbols to the footprints. We've done that. We've generated it. Edit symbol fields. Fuck that. BOM cost? Nah. Run PCB new. This is going to be the layout. So we open this up. It's interesting. The schematic is a light theme. The PCB is a dark theme. That's just the defaults that the KiCad comes with. So we have to import. Here we go. So update PCB from schematics. We're going to do that. And it says, okay, we got to get all these changes. And this process is a little bit cumbersome, but it's gotten so much better over the years. Because like this used to be really painful back in like the KiCad 3 and 4 days. This is version 5 that I'm using. So because this is fresh, I can just keep all these defaults the way they are. Update PCB, and look at that. Cool. Here are my parts. So this is going to be for the 7-segment display, and what I will probably do is create a little adapter board out of like perf board or something that just kind of like sits in here. This guy, these are just breakout for spare pins. Here's my little microcontroller, a little jumper for selecting power, I think. Zoom in, you can see the signals. Yeah. This is for I2C. This is the shift register itself. this is the input power. And then these are all little capacitors and diodes and so on and so forth. Actually, I don't have any diodes in here. Capacitors and a couple resistors. 2 resistors, in fact. Oh, Dan, if you're still watching, I was just thinking about some of the analog circuit stuff that you're designing, and that actually might be a really interesting thing to explore, is the fact that, like, yeah, you have, depending on the type of capacitors that you use, if you have a whole bunch of, like, RC time constants, especially if you're doing, like, 555 timer stuff, then, yeah, depending on the types and values of capacitors that you pick, that might actually affect the expected versus actual, like, you know, performance of your circuit. So that's kind of interesting. All right, so bypass capacitors, you want to put them as close as you can to, you know, whatever it is that they're bypassing. So I'm gonna control click here, and that highlights these things. So if I look at, I'm gonna dual screen this. Let's see, I'll swap these, because the schematic is a reference, the board is the canvas. All right, so this guy, I've got C1 and C2, but shh, I'm putting C5 here, don't tell anyone. They're all the same value, so I'm gonna get sloppy. Ooh, actually no, it's cross-probing for me. I think I will just do what it says. Okay, fine. All right, this one goes to U3. U3 is one of these little LDOs over here. Wait a minute. 3.3 volts. So I'm wondering if there's a way that I could potentially not power it through this thing and just inject 3.3 volts just directly into that, but I don't know where I'm getting power from, and I'm tired and I don't really care, so I'm not gonna change anything. Yeah. So hotkeys, oops. What is it? T? No. P? No. How do I put a trace down? Single track. Shift X. I guess. Okay, let's get the I squared C up in here, up in here. Okay, so also I would like to avoid too many vias if possible. Um, that's just kind of a little design preference thing, but it also means if there aren't any vias and I can keep this all on like one layer, then that allows it to be potentially hand etched if I wanted to do that. So that'd be kind of cool. Alright, so this guy, that'll go there. Okay, I don't need to do Shift X, I can just press X. So that's good. Okay. So this guy, these are the power pins. And the power pins. What's that? Pin 6, 3.3 volts. A bit different from 3v3. What's going on? Pin 6 is what? Huh. It's unfortunate. It seems to think that 3.3 and 3v3 are the same thing. Well, I guess technically they are. I should probably just put a better LDO on here. I wonder if I could just do that. Yeah, okay. Fuck it, why not? So what we're gonna do is we're gonna create a power OR and do LDO load sharing. So we're gonna do, let's see, custom Schottky diode there. So I'm gonna get rid of this. Oops. I like 3.3 volts instead of 3v3 actually. So the same guy who originally showed me all these capacitor things, he was actually he's like what, in his late 70s, but incredibly smart guy and super sharp too, like, you know, really just on point, and like still routes boards, does all this kind of stuff, still you know, still super active. He rows and flies planes and all that kind of stuff, but he has been in Silicon Valley his entire life, just doing all sorts of crazy cool things. And he was telling me that the reason why all these like things say like 1v8 and 3v3 and all that kind of stuff is because like the early EDA tools for doing like schematic capture and board layout stuff, they couldn't support decimal places. So you couldn't have a decimal place in a string like this, or else it would crash the program. So they had to come up with a way to sort of like represent that. And it's like, you know, you think about nowadays when it's like, you know, you have Unicode and you can have like emojis and weird diacritics and stuff in your strings, but yeah, you could not do that back in the day. All right, so here's what we're doing. We have two LDOs, both being powered from the same rail, going into these Schottky diodes. So Schottky diodes are designed such that they have like a low forward voltage drop. So like what's coming out here is probably going to be like I don't know, a little under 3.3, probably going to be like 3.1 or 3.2. I forget. I think the forward voltage drop in a Schottky diode is supposedly pretty small. Not supposedly, it's measurably small. Smaller than like a standard PN junction, which is your standard, like, what is it, 2N 1000 something, like whatever those, again, more jelly bean diodes. So if I go ahead and delete that guy, do this, I'm gonna do this, we're gonna buy these parts and populate them, and by God, if this doesn't work, we'll just make another one. All right. So I will save this. I will annotate. There we go. Added those things. Close them. Save and import. Oh, no footprint. Oops. Good catch. Rule checker. No, I don't want that. Crepe. We'll just double click on that guy. And then there should be some standard packages for diodes. Diode SMD. And then SOD. Small outline diode, I think. Schottky diodes. Diodes, rectifiers, single, active, in stock, cut tape, Schottky. Whoa. FERD, field effect rectifier diode? Hold up. What the fuck is a FERD? Never heard of that before. Field effect rectifiers. Is this new? Sorry guys, I just need to go down this rabbit hole real quick. Field effect. So, okay, I accept your cookies. Okay, so there is always this concept of the ideal diode, or ideal circuit components and stuff, where it's like, you know, when it's forward biased, it's, you know, there's no voltage drop and it's perfect and it has this sort of like hockey stick shaped curve. But in the real world, you always have some non-idealities. And like the Schottky diode is to get away from some of those non-idealities of like standard PN junction diodes. But this is cool because if this is a field effect rectifier diode, I'm wondering if, wow, 30 amps, 100 volts, pretty beefy. I'm wondering if this functions a little bit more like an ideal diode, right? Where it's like, it's field effect, so when you like have it forward biased or whatever, it creates a, like, you know, a P channel or an N channel, something like that, like you have in a transistor, but it allows like, you know, current to flow with just like a very, very low, ultra low leakage current, medium forward voltage drop. Down the first with a decrease in the voltage drop and a decrease in leakage current. Wow. As a result, the runaway safety margin is improved and maybe beyond the typical safety margin of Schottky barrier diodes. Wow. That's cool. Okay, well, I'll put that in my back pocket and think about it some more later. Seems exotic. Exotic things are expensive, but sometimes necessary. So if I'm looking at the cheapest things here, it's 15 cents. That's cool. I don't need a lot. 250 milliamps is what those things can provide. So I probably want them 300 milliamps or more. So, up to 50 amps. Do something like that. Just kind of spec it out. Oh wow, there's only 4 million of these things in stock. What will I do? SOD 323 works for me. This is the one. Okay. Sounds good. Sounds good. Okay, so that's been applied. Let's go back here. Let's see if it errors out. No errors. That's good. Update PCB. Cool. Alrighty. Well, moving on. Alright. Excuse me for 1 second. I'll be right back. Alright. Well, Slack McGee, thank you for watching. I'm amazed anybody's watching at all. So, yeah, I'm glad you're getting a lot out of it. I appreciate the appreciate the message. All right, have a good night. I'll be right back. Sorry, just getting the essentials. Got my whiskey, but now I need some water. Hello again. All right. Okay, cool. So we got our Schottky barrier diodes in there, and they're ORed together. Yeah. And we are doing that so we can double up on the thing. double up on the regulators here. Just gang them together, or whatever, not populate them and put a different regulator entirely on there. This board is going to have a lot of manual reworks, I predict. Some people call it white wiring. Some people call it blue wiring. Some people call it bodge wiring. But in any case, it's just fixing your fuck-ups and putting a whole bunch of extra air wires on top of this thing. So if this goes like this, here's what we're gonna do. This is gonna go here. So okay, normally what you'd want to do if you were actually like, you know, I don't know, professionally doing this, you'd want to put down some like ground planes and oh my god, this is my cat MOSFET. Meow. Sorry. MOSFET, come here. All right, hold on. I'm gonna get MOSFET. Oh goodness. MOSFET is a chunker. He is a bigger boy, but he is a cuter boy. All right, get that cat tax. All right. Yeah, I know. All right, there you go, bud. Yeah, that connector is massive compared to the chip. Yeah, like that's a 3-pin connector. Like, so this is the bag of bag of chips that I ordered, and holy mother of God, these things are tiny. So like, what's gonna be awesome, right? So I'm trying to show you the size of these things. I don't know if it's gonna like show up on here, but like, they are smaller than my fingernail, like in this reel. I don't know if that's coming through. Hopefully it is. But they're teeny tiny chips. And as you can see on these like 7-segment displays, like relative comparison, like they fit within the footprint of the 7-segment display. So it would be cool to be able to, like, you essentially have a board that is just wide enough to mount the through-hole 7-segment display on, and then on the bottom side of it you have the chip, and like, boom, there you go. And they just have like little like connectors, edge connectors that allow them to like connect together, so they can be like this flush mounted thing. So that could be neat, but I digress. Why does... Oh, alright, so this is the VDDIO. VDDIO, it's off to work we go. Alright, so in order to not have any vias, we're going to make the board larger than it necessarily could be. Right, so this guy, gotta squeeze that in there. The shift register is larger than the chip. Like, that's ridiculous. Alright, I want to see if I could get a... Oh, yeah. The default routing rules let me get a trace in there. Very nice. Okay. Control Z that. What? Alright. I want to... drag this thing. And I forgot there's a setting, route, interactive router settings. Yeah. Okay. Aha, mouse drag behavior, move item, interactive drag. That's it. So this is cool. So Dan, this is kind of interesting. So this is like, um, it's not like manual versus automatic. Like this is sort of like a semi-auto uh, auto router, right? So this sort of like determines like how optimized of a path do you want as you're like moving things around, and like laying out your traces. Um, so you can set it to be like you know ultra low effort. I don't feel like moving things. I'm just gonna leave it where it is. Or like super high effort to like jiggle things around to like I've got to put like in order to get this trace through these two vias, I have to move this via and move that via, but that means moving these traces, which means moving these other vias, and it sort of like propagates out the amount of work that needs to be done for really really dense boards. There we go. Cool. So now we have an interactive drag. So there we go. Cool, cool. And this is a style thing. This is not actually like, oh, it's a clock. Sometimes clocks are high speed. This is not high speed. This is going to be clocking out at like the most at like, a megahertz or something like that. Not even that. Like these are LEDs. So what persistence of vision gives you, you get it at like what, 30, we'll say 30 updates a second. 50 updates a second because we're blindingly fast here. Then you're gonna get like your 50 updates a second. Oh fuck, I can't even do math right now. 8 bits. So you would need 8 times that for 100 bits a second, which is not fast. Point of all that. All right. Cool. You know what? We're gonna have to put some vias in here because this needs to get out the door. God damn it. Okay. Well, fuck it. Yes, fuck it. Well, I've decided, because we're putting vias in, what is that? Unroute. Oh, if I hit U, it selects the entire thing. Oh, and I can delete it. Oh, that's cool. Okay, cool. All right. X to do this, and then we're gonna go under. So how do we do that? Two. Come on, there's gotta be a hotkey for switching layers. Gotta be. View. Alright, I'm gonna Google this real quick because it's kind of a usability thing that I need to figure out. KiCad, switch layers keyboard. 66 shortcuts. is question mark. That might be a good place to start. Switch units. Set local coordinates. Hello, Buan. Buan is the other cat. Okay, so I guess if you... Maybe if you just do V while you're... V adds a via. So we do that, I hit V, and it's like, all right, cool. I'll drop that. All right, cool, and it automatically changes the layer. I am fine with this. Via, yeah, cool, good enough. Now these guys are fucking huge. All right, so this is a 15 mil via, well, a 31.5 mil via with a 15 mil hole, 15 mil drill. Generally speaking, your PCB manufacturers are going to have certain limitations on the sizes, the size of a mechanical hole that they can drill, and a lot of them will go down to maybe 6 mils, like 6/1000ths of an inch, for a mechanical drill. Some of them will stop at 7 or 8, but it's somewhere on that order. And if you go any smaller than that, they have to switch processes, and they use lasers to drill those holes. And when you use lasers to drill those holes, that becomes, they call it HDI, or high density interconnect, and it is much more expensive, is the point of all that. So you want to try to use the mechanical drill process as much as you can, unless it's absolutely necessary. Sometimes it is, and that's why those processes exist. But for a cheap throwaway board like this, big vias, get out of there. You do not want to eat those things. Sorry, I'm talking to the cat. Yeah, for most prototyping stuff, you really don't want to go into advanced processes, because it's not something that JLC PCB is going to be able to do. So, oh my god, Buon is going to knock over my whiskey. I'm going to be so pissed. All right, so kind of stretching that out a little bit. Also, so if this is, again, not something to pay attention to here, but something to pay attention to, in your general, circuit design engineering stuff. Ooh, well, I'm going to delete that, bring it back in a bit. Oh, you go to bed. Is that, so a via, as you can see, is a hole. But it's also it's a tube, right? So you have these traces that are pieces of copper, and a signal is going to start here and moving real fast at the speed of light in copper. It's going to propagate through here. Sorry, I wish I could show you what I'm gesturing to on my screen, but I guess it's gonna have to do with the mouse. But yeah, so you have this, you'll have a pulse, it'll propagate through this thing, I guess from here, that way, and it'll go into the vias, and the vias, they are not just pure interconnects, they actually have inductance to them. So that is a potential problem if you're dealing with really high speed stuff. But that's sort of when you're getting into the tens, hundreds of megahertz, gigahertz type things. Everything here is slow speed and prototypical, so we don't care. But because it's the kind of thing where oh yeah, you do want to put in you're adding inductance to this line here, And I, have to get out of this mindset of, uh, like, oh, like, it has to be perfect, it has to be professionally made, when really that's not true. It's like this is designed to be a piece of hot steaming garbage, and it needs to be quick and dirty and out the door by tomorrow, rather than being something that is perfect and could work up to a billion hertz if I needed to, because it doesn't. So I mean, like, part of what the design process, the engineering process, is like, design for the application at hand, right? It's like you can make the most general purpose thing in the world, but it's like the most general purpose thing in the world is not going to be good at anything as the thing that is purpose built. So you want to purpose build your designs and make them just good enough, and that way you can iterate on them. All right, so this thing is going to, oh, what's that? Okay, I got my Altium hotkeys burned into my mind. So in Altium, they have a place menu, kind of like this one up here. So like if you press P, that's place, and then T is trace, so you do PT. So I have the muscle memory for PT because my pointer finger and pinky finger sit right at PT on the keyboard, P and T, respectively. But in Altium, or in KiCad, I have to remember that it's X, which is annoying. But honestly, there are so many things wrong with Altium that, like, I can forgive KiCad for mildly inconveniencing me by not being like Altium. Altium, Altium is it's a professional tool, but they just, I don't know, they just don't have good management, or they don't have good people, or something. I don't know, because we use their they call it the Nexus system, right? And this is the biggest marketing clusterfuck I have ever seen, right? So it started off as yes, they have a tool called Vault, and Altium Vault makes sense. It's a place where you keep your component libraries. Oh, that's a reasonable thing to call it. And then they're like, all right, so we're gonna rename it. We're gonna call it Nexus, and it's like, oh, okay, that's fine. Do what you got to do. Confusing to some people, but whatever, marketing people. And then they're like, okay, Nexus is going to have two components. There's going to be a Nexus server and a Nexus client, and that's going to be like Altium Designer and Altium Vault. And Altium Nexus client is basically just Altium reskinned to have the Nexus branding on it or something like that. And then they're like, okay, this isn't working out, so we're going to remove it from our product offerings. So now they no longer have, so you can have the Nexus client, the Nexus server, which was formerly named Vault, and then they have the Nexus system, which is neither of those tools, but it is basically using those two tools with an additional layer of some sort of workflow management on top of it that they don't offer to most people. That's more for the mega bajillion billion-dollar corporations, and they help you figure out workflows and stuff like that. But it's it's so confusing and so hard to use that it's been just a tremendous pain. And it's Altium Designer is a fine product. It's a fine tool. There's really, it does a lot of stuff really well, and whatever, as long as they stick within their core competencies. But their component management system is just a hot steaming pile of garbage. absolutely terrible. What? Oh, oops. Whoop. Cool. All right. So we got a VIA and V. That's the same in Altium, which is nice. Actually, kinda. You hit PV to place a VIA, but if you're routing, and this is, I guess, this is one of those things where it's like I'm just used to in Altium. It's not actually sensical, but when you are routing and it's like, oh, I'm on one layer and I want to drop to another layer while I'm in the middle of routing, rather than like stop and put a VIA down and enter the interactive routing tool again and all that kind of stuff. What you can do is you have to have a keyboard with a numpad on it, and if you hit the asterisk button or the asterisk key, then as you can see here, so as I'm pushing the that VIA around, that's sort of like that's the optimizer kind of figuring out how to move those things around, the semi-auto router. But if you hit the asterisk key, that will jump to the next routable layer and place a VIA getting you to that next layer. And it's like, why does Altium do that? Why that key? Who knows? V. I don't know. The hotkeys are powerful, but confusing. Whoa, where is this even going? What is that? What does this even mean? Oh, that's VCCD. Oh fuck! I gotta put a capacitor in here. Oops. Man, it's been a long week of pushing a lot of copper. I am very tired. But the show must go on. Come on. There we go. What would I like to do here? Okay, so this is supposed to be VCCD. Yeah, you want your capacitors to be as close as possible to your actual device. So, I think I should really not I put no bypassing caps on this thing. Fuck it. Whatever. Okay. I'm gonna do this. Select this. You selects that whole thing. Oh my gosh. Okay. It deletes that. This guy. That's gonna move down here. This guy is gonna squeeze in here. All right. Something like that. Cool. We don't even need that VIA. Get rid of it. I think, so this is going to be a two-sided board because I don't even know if GLC PCB does one-sided boards. That's kind of like, that's something you find in like ultra cost sensitive type applications. Cost sensitive, cheap shit. There we go. Come on. Yeah. Okay. Yeah, so it's going to be a two-layer PCB. And then what we're going to do is essentially anywhere that you have ground, what we're going to do is just drop a via down next to it, and then it's going to connect to a ground plane on the bottom, and then I don't even know if I want to bother with a ground plane on the top. But the ground planes and all that kind of stuff, that just lets you helps reduce like EMI, your interference and stuff, but it also means that like you don't have to like have these traces all running across to your different things. All you have to do is just like, all I'm doing is plopping a via down, and boom. I just assume that at some point in time it's going to connect to a ground plane. So it's just a simplification strategy, I guess. I don't know what I'm talking about. So this is what the fuck? Get out of here. Okay, ground, do this. This guy, what I'll probably do is like, you want to have, this, that looks like it's connected, but I would also like to put that there. And you can have ground vias in, especially like high temperature components and stuff, and they help dissipate heat because they provide connection to like another plane of copper that can yoink heat away. But honestly, I don't think these chips are going to get particularly hot. I don't think a 24 megahertz clock in an ultra low power Cortex M0 is going to be dissipating too much heat. But that's just me. What I would ideally like to do, however, is like, I want to push these things to their freaking breaking point. So if it is possible to get these things like under their own like power, not doing anything too particularly ridiculous, get these things to like overheat, and they need some sort of like, or like overclock them somehow, like that would be pretty cool. I would be into that. Let's see, what is this? It's doing the cross probing thing. Okay, that's cool. Okay. Come on. Da 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 da. Yeah. So, Dan did mention something that I wanted to try, and I don't actually know how to do this yet because I'm still a noob. But what I would like is to just have some like background music playing, and I'm learning how to use OBS Studio a little bit better, and kind of see where that's like, how that could fit in. And I also found this is kind of cool. So like, I'm not a fan of getting sued, as most people are not. So I was thinking like, it would be nice if the music could be like Creative Commons, and there are some sites like Jamendo, and like I used that like a little bit a couple years ago, but they've sort of changed their whole I don't know, business model, I guess, of oh, come on, you. They changed their whole business model to like, they now like sell Creative Commons royalty free music type things, which is kind of cool. So you can buy a song, or you can buy a membership and like use all their stuff for copyright free music. All right, so what I like to do. Active router settings. No, it's going to be under in like tools, place, router settings. No, be like board configuration, board setup. There we go. Yeah. So that's cool. You can do Ah, there you go. That's cool. Two layers, parts on front. Nice. All right. So what is this? I mean, two layers, parts on front. Nice. Very nice. That's really cool. Oh, text and graphics. That's cool. I'm discovering new things. Yeah, and like that's you know, Patrick's story time. These tools, like, they're so complicated, so complex. Like, it's you know amazing that like free ones can even exist. Free open source ones can even exist. They're very complicated tools, and I find that like even especially things like Altium, where like Altium is one of these tools that has been around since what, the 80s, the 70s, I think. I don't know, something like that. It used to be called Protel. Um, it's gone through several different like uh, you know parent company acquisitions and so on and so forth, and uh, like it's also been rebranded a whole bunch, and they've had they had this weird phase where they like thought that everything was going to be FPGAs, and I don't know. They kind of went through a thing with they had a product called Tasking, which was supposed to be like their integrated development environment for like FPGA type stuff. Yeah, which like I don't know. I'm sure people still use it in industry, but it is not listed on their products page anymore. So, but these programs are so big and have so much history and so much just like baggage to them that they have new things to be discovered every single day. They are just absolutely like labyrinthine. Come on. 25 mils. 25 mils. Let me do it. Can you let me do it? Footprints have some items on removed layers. B mask. What is B mask? Bottom paste mask. Yeah, fuck it. I don't care. I don't care. Alright. Can I do it? Can I do 25? Yeah, I can do 25. Okay, so the only sort of like thing that I'm doing here is like for power traces, I'm making them thicker, and for signal traces, I'm making them thinner. Oh, okay, well, if it'll let me. So what you saw there, there we go, predefined widths. Cool. I created a new design rule. Let me do that. So they don't need to be this thick. 25 mils is a lot. Oh, look at that. If you're still streaming with OBS, just try opening this link. So I got my headphones on, and I will be listening to the lo-fi hip-hop radio, beats to relax and study to. But let's see. Audio capture. Actually, you know what I can do? My desktop audio. Yeah, okay. Yeah, I can see if I can do that. I'll pipe it in. Nice. Okay. Cool sources. And then, yeah, that works.
Sometimes, like, you wish, like, this sounds so dark and morbid, but sometimes you're like, boy, I wish I could just go on a college pause because I need a break from life.
How about that? That's pretty cool. Turn the mic up, the audio down a little. So my mic is on full. Alright, how's that? This is nice. These are lo-fi beats to study and relax to. Alright, it's good. This is really nice. This is Rochelle.
When you're asleep, you can't be
What's up?
depressed, you can't be sad, you can't be anything. When you're asleep, it's
What's
almost
up?
like you're dead without having the commitment to it.
Wait, why is it going through your this?
What are you talking about? So Rochelle knows more about this stuff than I do.
Oh, there you go. Wait, this is your mic.
Yeah, it's my mic.
Make this lower.
Oh, my mic is too loud? This is my mic.
Oh, it is.
Yeah, so the desktop audio over here. This is the
What's this loud ass fuck thing? That's mic.
yeah, the loudest fuck thing is the microphone.
Then what's
The desktop
this?
audio.
What's this loud ass fuck thing? Here, let me. Can I just turn this down? Turn this down. Yeah. Wait. No, keep.
Okay, keep it
playing it?
Okay. Yeah, I'll keep playing it. Okay.
Sorry, it was blasting in my ears. It's like really loud compared to my game and stuff. Oh no. Yeah, like, why is it so small? Oh, there you go.
So you're listening to my audio right now.
I'm listening to your stream right now, yeah.
Oh, little Daytona. Nice. You're gonna drive his dirt bike full speed into there without stopping. Wow, way to go, little Daytona.
This is okay, good enough.
Wait, is it? Okay. Well, cool. Well, thanks for the tweaks. I'm gonna get some more whiskey. All right, and I'm back. It's the same. We can't hear you. The music is too loud. Is there a compressor going on? Not just clipping. Make it half that, actually. I'm gonna adjust it on the... Let's see. What about that? Because I'm quieter. Okay. Did that help? No change. guys for helping me debug this. Like Ox. So. Oh, okay. What about that? Oh, switching songs. Oh, much better. Okay, cool. There we go. Wait. Wasn't sure. Oh yeah. it was just the end of the song. All right. Well, just to you can't hear music. Oh my goodness. Oh my goodness. What about that? Okay. By the way, thank you guys for helping me debug these these streaming pains. Okay, the levels are now good. Just set 5 ever. I'm gonna do you one better. I'm gonna take a screenshot of my levels so that I can recreate them in the future. I have no idea how this shit works. He's always crying. All right. Root. Screenshotting settings. You're way too practical. Well, it's because I know I'm gonna fuck up again. My file directory. Oh no, are they gonna hack me? Am I gonna get hacked? Oh no! Oh no! Listen, that folder labeled hentai, that's where I keep all of my homework. It's so that nobody steals my homework. Alright. Let's get this road on the show. I gotta place these little fuckers. So these guys here, these are our LDOs, low drop out regulators. Oh shit. Whoa, you guys, your IP's localhost? It's mine too. My password is Hunter2, by the way. Please no one hack me. Where are my inputs here? Where's VCC? So this is super nice. So this feature here, so I don't know if you can see. When you click on it on like the schematic side and it highlights it over in the PCB side, that's called cross probing, and it's something that you get for free in KiCad, but you have to enable that feature in Altium if you do such things. Yeah. What was your password? All I heard was asterisks. Yeah. Well, Mr. Martin, I will I'll play with those settings a little bit later. I just want to finish up this board, so we'll experiment with that on another stream, I think. But in the meantime, we'll just leave some of these chill beats subtle and muted. All right. So, all right. I want to put this guy. This is the VCC. This is power input. I'm gonna put this guy over here. I squared C. So this is I squared C connector. That'll sit here. Cool. VCC power. Put over. Yeah, we'll do this. So this will be the power regulator area. All those lines. Yeah. So like, somebody was talking at work about like, oh yeah, so if like, you have these like gross oversimplifications of like what you do every day and stuff, and it's like, what like a I don't know, programmer would be like, oh yeah, just like, I hit buttons and I make like lights change on the screen. But it's like, yeah, for this stuff it's like I'm just moving rectangles, like it's just pushing lines around, that's all it is. It's basically just like spaghetti Lego. Ooh, all right. Well, Pusoko, thank you for coming in and helping folks fill in the gaps. I appreciate that. All right. Nice. So this guy, so we're like, so we have, I'm gonna put some capacitors up here by the, it's just the input power or whatever, so. That'll go there. And then wait a second. That's C12, that C2 and C3. Yeah, so these things will go over here. C2, it's over here. Cross probing is a really nice feature. It just sort of lets you keep track of where everything is. Spaghetti Lego. Yeah. So, even if, you're not totally sure what's going on here with the, the lines and what they mean and all that kind of stuff, it's kind of like when you watch, was it Bob Ross, it's like the Happy Little Trees. It's like, I can't paint for shit, and I sure as hell I'm not gonna get a canvas and start painting, but I could, because everyone can paint. You just get to watch me make all these like happy little accidents, and it's just kind of you get to just be part of the experience, and that's what makes it fun. all the accidents are they're very unhappy accidents. If you connect something wrong, it'll just not work. There's less forgiving than the happy little trees. That is for sure. So these guys, so what I'm doing here is, you can think of like capacitors as little like, buckets for electrons, and you want to make sure that you have large enough buckets for all of the electrons flowing through your circuits. They kind of like buffer things out. And these guys are little voltage regulators. These little 3-pin parts. And those guys will take an external voltage, so like you hook up a 9-volt battery or something to this circuit, and rather than causing the thing to explode and catch fire, it drops it down to a more manageable, like 3.3 volts. That's the idea anyway. Yeah, that looks pretty good. There's a Bob Ross Twitch emoji. That's awesome. Oh yeah. Oh, I need the. I need some sort of like. Just that some sort of equivalent of Bob Ross when he does the like the flap 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 of the paintbrushes. Maybe when I'm putting the circuit together, I'll live stream that, and I'll just like, I don't know, smack the circuit board against the wall or something. Yeah. Look at that. All right, cool. Connected. And then these guys. This, I'm going to drop a via. Oh. And the nice thing about through-hole parts, I don't say this often because I don't really like through-hole parts, is that if you have a connector or something like this, you don't have to put vias in, or as many, because they're already, you know, through holes, and that's kind of what the vias are buying you. It's sort of like a through hole to another layer. And if you come on now, I just wanna, there you go. Yeah. Yeah, so you get like, you know, you can connect these traces on the backside. But I also find that if you're soldering stuff by hand and like just learning how to solder and whatever, then let's see. So the white lines are like cheat sheet connections. Yeah, that's a good analogy. Yeah, so the red lines are actual copper. Red is, that's copper on the top layer. So you can think of it like a sandwich. So there's copper on the top and then some fiberglass in the middle. And then there's more copper on the bottom. And the copper on the bottom layer is represented with a green line. Yeah! Cool. So then, boop, add that. Come on now. There we go. Very nice. So I squared C is connected. I'm going to put a couple of ground vias here just to kind of clean things up a bit. Make them nice and well connected. Nice. I'm really liking these lo-fi hip-hop chill beats to study and relax to. No, wow. Part disappeared. Okay. Ground everything or you're grounded. I keep losing my part. Want R. Yeah. Okay. So we have so much space. There's no reason to get stingy here with space. Oh, nice. Like the redstone in Minecraft. Yeah, that makes sense. Oh, this is totally like painting for engineers. This is MS Paint. It's like, you know, you have the drawing tool in Paint, where like, you know, you can draw all sorts of like crazy squiggles and stuff. It's like our lines are like there are 45-degree angles. Like anything more than that, it's like that's a little too much for us. So it's yeah. I'm not tipsy. That tipsy. Yeah. It's been a long week. I deserve this. Oh yeah. So like back in the day, what they used to do is like they would have like those light tables, and so it's like the desk with the you know, projecting light underneath it, kind of like a drafting table or whatever. And they had stickers that they would like stick down on this like drafting table or whatever, and they would like draw out all these circuits by like sticking down, you know, little pieces of tape, you know, to make these, you know, these circuit boards. And this was something on the order of like, it was, you know, you tape it out in large scales, would be on a big, like the size of a desk, and then it was a photolithographic transfer process. So they would take that desk and then they would project it and then shrink it down, kind of like you do. What is it? Sort of like the reverse process with like developing photography. But yeah, it was just like you take that big honking thing and it's like, oh, there's your circuit board. And it's like, oh, you made a mistake. It's like it's gonna be 6 weeks before you can fix that mistake. Yeah, for architecture. So we're seeing 9 and 10 going. Those are the VCC inputs for U4. Yeah, nice. Put that over there. C13 and 14. So these guys. So these little white outlines here, those are called courtyards. Not all footprints have those. They make it really easy and to kind of, I don't know, space your things out. So if you have, like, I'm populating these things by hand, but if you have a machine that's like, you know, they call them pick and place machines, then you can like put these things super close together, and they have little like robot suction cup that like will just pick one up and put it down and, you know, put them in the right spot, and you can like cluster them really close together. But the white outlines are just sort of like general guidelines for when you're like placing components down. They don't actually show up in the manufactured board. All right, so move this on up. Put this in here somewhere. What's the purpose of the device you're designing? Ooh, I get to talk about this again. This is... Let's see if I can find a bag. Yeah. So I bought a bag of microcontrollers, and there's these like little teeny tiny like little chiclet type things in here. And they were very, very inexpensive microcontrollers. So you can think of it kind of like an Arduino or something like that if you've ever played with those. And they're like 50 cents a piece or something like that, which is like, you know, abnormally cheap. And I've been talking with a few friends of mine about this computer that was like, it was basically somebody's, I don't know, PhD thesis or something like that, you know, back in the 80s, called the connection machine. And it was this idea that like, oh, instead of having like, you know, in your own computer right now, you got a big beefy boy processor that runs at 3 gigahertz or something like that. What if instead you had like 100, super, like, or you had like a whole bunch of really inexpensive microprocessors, and you could break apart your computational load in such a way that you could just send it to all these different things, a massively parallel computer. And this dude like made this computer. He got some funding and was able to create it, and they called it the connection machine. And it is something that I think it's a cool idea, and it would be neat to sort of like play around with, like, it's basically just to like experiment with like computer architectures type thing, and see if you can find a way to like write software that is massively parallel like this. So this is kind of just like the shit nerds do for fun. But this is a breakout board essentially for those microcontrollers. So this is the microcontroller footprint. It's this little like teeny tiny guy right here. And ooh, yeah, I think I can put this into 3D view to show you guys. So this is kind of nice. So I'm gonna put these a little bit closer just to kind of, for effect. And then I can do 3D viewer. Yeah. So this is kind of what the printed circuit board's going to look like. So this guy's going to, move down, but like this thing is kind of the little breakout board. Yeah, so like, saying it's a huge undertaking, it's like, yeah, like it is. Yeah, if you want to make something that, is, functional and works super well and is a general purpose computing machine and supercomputer type thing, that's a big undertaking. But I like to like fuck around with these things and just put one on a board and see if you can get it to light up some LEDs. It's it's relatively easy to do, and if time is not a huge issue, then building something like this isn't the undertaking is a lot less. So that's kind of what I'm relying on here is like, it's just something to play around with and see if you can get it to do something cool and maybe write I don't know, write a blog post about it or something. But as far as making like the next big supercomputer, I don't know about that, but it's just kind of a way to have fun in the meantime. How do custom parts look in the 3D view? Well, so custom parts. All that is a it's a step file viewer. So if the custom parts that you build, if you have a 3D step model that you import into your parts, then it'll show up in that 3D viewer. So you can use a CAD tool like SolidWorks or I don't know what the other one is. The one that KiCad recommends is FreeCAD, which is like super cool because it's this it's a parametric CAD modeler, kind of like SolidWorks, but like all open source and like does a lot of stuff. So it's like people have built like toolboxes that like do architecture, or they can do what else? Like finite element analysis type stuff, which is like, if you need to see kind of like what, do like aerodynamics or like stress analysis for, mechanical design, these sorts of things. Like it's a very versatile, very awesome free tool to, mess around with 3D modeling. And it's kind of like, you have like Blender if you're doing like sort of your artistic or creative stuff. Oh, yeah. So here's the thing. So SolveSpace, there is a SolveSpace workbench in FreeCAD. Like, there is an OpenSCAD workbench in FreeCAD. So like you can import your solve space and like other open source like parametric modeling tools, you can import them into FreeCAD. Listen, you can get out of here, Pusoko, with your scatological talking. Just kidding. I like poo-poo humor. Open SCAD. Open SCAD. It is this thing. I will post a link to it. But it's basically like... Wait, what? Yeah, I have yet to play with Fusion 360, but I hear a bunch of people use it and like really like it. So I have yet to give it a try. I just don't do a lot of like, you know, parametric modeling myself, but that's cool. Oh yeah, solve space. I think I'm gonna pull this over here. So solve space is who does this? This is White Quark, isn't it? No, wait, Jonathan Westhughes. Yeah. Oh, it's now maintained by White Quark. Yeah. So this person does a bunch of really cool stuff in the open source FPGA space. This person does like freaking I guess quantum computing for their day job, and then open source FPGA stuff for, you know, their free time or whatever. But yeah, they're the maintainer of Solve Space. They do really cool things. So I follow them on Twitter. But yeah, I think I don't know which one's better. FreeCAD is the one that KiCad uses for their kind of like 3D modeling backend, I think. But I don't know which one's best. Who knows? Maybe Dan knows. Maybe it is Solve Space. All right. So I'm putting all these traces down. Okay, connect. I'm gonna draw these guys. V for Vendetta, and also for V as to ground. Okay. All right. So I think what I'm gonna do, because the output of this is where it goes from Legos to Tetris, and you know, you think about it like you have this like, you know, all these things that you need to connect, but you only have like, you know, a couple planes to connect them, and there's a lot of like, you know, visual problem solving going on here. So you gotta kind of like move things around and be like, yes, if I move this thing and rotate it to there, that gives me more room here, and then this part can go over here, which means that these guys can go over here, and it's like it's all just a big old I don't know, what do you call it? Like, it's like one of those puzzles where you have like, it's like a 4x4 square, but they take one of the pieces out and you can like jumble it all up and stuff. And then you have to solve the puzzle. Get out of there, tiny little trace. Do, 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 do. Oops. Oh, nice. Legend of Zelda Wind Waker had that mini game in a house. That's pretty cool. See, I don't want that ground trace there. I don't need a via to it because it's already a through hole. Maybe put this here. Ooh. All right. So these guys, they need to be moved down. Yeah. So connectors are nice because they have, so let me kind of read this out loud. So yeah, Dr. Martin made the point of saying, like, for, you know, most of the parts anyway, they're not that complex, black box and sometimes some additional pins. Yeah, like that's true. But sometimes, so for the most part, that'll get you there. Something that we do occasionally for our work is, like, we'll use the 3D models to, like, once they're on the board, they are they're exported as a step model, so you can incorporate it into, like, the 3D models of some bigger assembly. So if this is like going into a robot or something like that, then you can like see how it like integrates. So if there's any like interference fits, because a lot of time, like, things like inductors and stuff are really tall, and, you know, if they're being fit into like a super tight space, then you know, you can have issues. So we, rather than be like purely aesthetic, we use them for like mechanical fit checking. But yeah, for the most part, like, connectors are good because manufacturers will include 3D models for them. For a lot of the, like, little black box packages, like the you know, for like this guy here, this shift register, and for this microcontroller, they don't include that stuff. They have, like, they'll say things like, it's compliant with like IEC 7351 or something like that, which is like a standard for how you build surface mount components, but they won't actually include any 3D models. So, like, you either have to generate them or build them yourself, or download them from, you know, what is it, Easy Snap EDA, yeah, they're one that does that. And they have a service that like builds these parts. But library management is like, it's a nightmare. It's a horrible thing, and it's something that like, it's a dirty little secret of the electronics industry. Is like no one has figured out how to do library management well for electronics design, and it's sad and very frustrating. But yeah, that's something that like it means there's lots of room for innovation in that space, I guess. Nice. Manufacturer libraries, easy to come by. So manufacturer libraries, no manufacturer is going to give you the printed circuit board footprint for an electronics component. They would give you a 3D model for their part if it's a particularly weird one. So weird being like, connectors. So generally connector folks are really good about that. Also things like inductors or like solder in modules and those kinds of things. Those are generally pretty easy to get 3D models for. You find them on the manufacturer website and stuff. As far as not complete libs, but 3D models for sure. What is that picture? Oh yeah, I'm looking at the what is it? The 4x4 picture thingy that Pusoko posted. Nice, yeah. So like often or pretty much exclusively in the data sheets, you'll just find dimensions. So like I'll pull this up for this thing here. Like the only thing you'll really have to go on is something like this. So they're mechanical drawings, right? And they'll show you like, spacing and pitch and, tolerance and all that kind of stuff. And like, if they're nice, sometimes they'll say, build this footprint. This is the footprint you want for the package that is presented above. But they don't always do that. And like sometimes they're conformant to some specification, other times it's like I don't know, the manufacturers are just playing fast and loose, and they make their own electronics packages somehow and do some weird stuff, and they're like, yeah, just make this weird thing. So a lot of the times for the parts that we make in our company, if it conforms to a particular standard, like in this case, TSSOP is common enough that it's been standardized by the IPC, which is like some electronics like standard body. You can parametrically define a part, so you put in like, yes, I will put in 36 and 1.26 and 0.65 and this spacing G here and H and C and D and so on from this table, and then it'll our EDA tool Altium will automatically generate the 3D model and the footprint for it. So that's more or less the process that we go through for like building up our library and stuff, but it's pretty tedious. It's still pretty tedious and pretty time consuming. Housing manufacturers also often provide models for their housings. Oh, some PCB outline. That's cool. Yeah, that's pretty cool. All right. Boop. Kind of like what it's looking like now. This is pretty nice. I am pleased with this result. So something that I might do, and this is also kind of nice. Like it's a cool like visualization, but it's also good for doing like board planning and what do they call it? I forget the word. I don't know, just planning where all of your parts and pieces are going. So like these capacitors here, I'm probably going to move those down a little bit. This capacitor, I'm probably going to move here, like over to the right and down to be nearer to that pin. And then that carves out this little section here, which means that this entire block can now be scooted down to be closer to EU2. And then the last thing that I would have to do for these boards is then just route these little traces to this connector. And that can kind of go off to the side. So that's what I'm going to do. By golly. I remember wondering before why there are unused pins and whatnot. Unused pins, Jather, are you talking about unused pins on the microcontroller, or like on the like LCD and stuff, or LED, I guess? Because a lot of the times, like these, like the packages, like they're standard packages, but they you can put whatever you want inside of them, right? So you can think of it like it's like a super teeny tiny little briefcase made out of epoxy for a piece of silicon. And a lot of the times, if your piece of silicon doesn't use all the pins in the briefcase, you can just leave them disconnected. So if there's like mechanical reasons or electrical reasons, you don't have to connect everything together. But it's just sort of like, and that's something that the industry kind of like figured out. I guess whatever, a couple decades ago, was like, back in the day, anybody can make their own weird, arbitrary package, and then it was really hard to like substitute in components and manage supply chains and all that kind of stuff. So what they did is they said, like, okay, we're gonna have a package that looks like this thing, and it's gonna have 14 pins, and it's gonna be relatively like whatever. It's gonna have a little cutout for your silicon die, and it's gonna sit like right here in the middle, and then you're gonna have some they normally have like really fine gold wire that will jump from the silicon die out to the actual physical pin pads, and then when you do that, you sort of like connect everything up, and then you put put the cap on it. It makes it a nice little like hermetically sealed package, which is why, so I will pull this up. There's a lot of like cool decapping videos and images. And you can see that like the silicon die is it is far smaller than the actual like package itself. So this is sort of like an electron microscope shot. That's from Dirty Decapping. Let me see if I can find a proper image here. Yeah. Normally to like decap this stuff, it's like the black chip package material is an epoxy, and you normally need to use like nitric acid to dissolve it away. Ah, yeah, there we go. Yeah, wow, that's a really nice die shot. Cool. Do you know what part that is? Huh. Very cool. Yeah, you can even see all like the bond wires and stuff coming off of there. That's really nice. Alright, well. Keep chugging along. Alright, let's do this. So I want this to be a little bit more in here. And we'll just connect it like that. No big deal. Cool, cool. All right. Then this trace, we'll delete that for now. And then this has nothing on it, so we'll scoot that out here. And then we'll take this big old chunk. Just kind of scoot that right on down. Yeah, like that. Looking good. Okay. And then these guys. Yeah, I think that's enough room. Okay. Scooting on down. All right, so that'll go there, and then this. Oh my goodness, we are approaching completion. So, these little like white lines that show just sort of like direct, cheat sheet connections from pad to pad kind of thing. So that is euphemistically referred to as the rat's nest, and the rat's nest, you can kind of like take this and you kind of like move it around. And you can get a sense for like, depending on like the position and orientation and stuff, what's the best way to connect all these things together. And you kind of get sort of a visual sense there. 3.3 volts. I need to connect these guys up. So I'm going to scoot down to the bottom layer. Drop a trace all the way around. There. Nicely connected. Beautiful. Gorgeous. Alright. So, there's this guy. Also, so there's a word that I learned recently, and it refers to like, say you got like, a whole bunch of like bendy bits in here, and like bendy bits and stuff for low speed signals is not really a big deal. You got to worry about reflections and stupid things like that for, high speed signals and so on, because it's like basically you can think of it as, the signal is like traveling along here and it's like, and it hits a corner. And as it hits a corner, right, the high speed, it's like it's an electromagnetic wave that's like propagating through this this copper here. It'll hit that, and most of it will sort of like move forward through the trace, but some of it will be reflected back, and that can affect the impedance at super high frequencies. But the term I learned for kind of like cleaning that up and making it look nice and stuff is called glossing. So if you gloss your traces over, makes them all pretty and aesthetically pleasing. Not necessarily any better, because it's like you think about like you're trying to design this well enough. It doesn't have to be super over engineered because these are all low speed signals and so forth. But it makes it pretty. That's the point. Okay. Cool. Just like that. So that side is routed. That's nice. Okay. We'll gloss these guys a little bit. Excellent. So, because that guy's there. I'm going to move this over here so I can connect to this guy directly. That's kind of nice. And this guy. So something that you can also do when you're doing this type of stuff is like you say like, oh, like anode B is going like all the way across here. Like, wouldn't it be nice if it was on this like this empty pin, you know, 5 or something like that? And you can, you know, especially if you're doing the schematic capture and the layout at the same time, you can, you know, you have the power to do so. But you can sort of like, you can swap these pins out and say like, okay, cool, like I want A and B to be on 5, and as you're routing, you can adjust the pin outs as you go, which is a, you know, a nice sort of freedom, you know, you get to do if you have control over the schematic. A lot of times, apparently, at like, you know, big companies and stuff, you do not. It's like one person does the layout, and that's it. That's the layout guy, and you must implement the schematic exactly as laid out, without like, you know, unless there's like a lot of process and cumbersome stuff involved. All right. Oh my goodness. Catch up here. Just Google. Come on now. It's kind of ugly, but perhaps necessary. It's like this wire here, I just need it to be somehow pushed down a little bit more. I think I'm going to delete that. I'm going to route this guy and figure out a way around it. Cool. I don't even need that. Okay, well, this is just going to be a really long trace. That's fine. I'm not interested in trace optimization right now. Cool. Okay. That's nice. That works. How many more do I need to do here? That needs to connect to that somehow. What if I had a big old beefy trace that ran around the whole thing? Terrible. I love it. Ground. So it looks like most of the connections are to ground. I think the only thing left that I need to do is, yeah, cool. Yeah, I just gotta connect VDDIO and then put a ground port on the bottom, and then it should be good. Nice. Last thing is, actually this is going to be an issue. So some of these guys are like they're isolated away from, like, even if you pour like a ground plane on here, it's like it wouldn't necessarily be able to flow. I guess you might be able to. There's just a lot of roundabout traces and stuff. So I don't know. We'll give it a try. Let's see if he gets all of our connections. So place, we're gonna place a zone. Get in the zone. Fillet radius, corner smoothing. Well, let's do a chamfer. Nah, just kidding. I want a rectangle. Pad connections, thermal reliefs. Thermal reliefs to plated through holes only. That's cool. Do 10 mils and 10 mils. So this is basically saying if you're soldering this stuff, if you have like a huge just, you know, plane of copper that is like, you know, that you're trying to attach your components to, you know, it's essentially a heat sink, right? Copper's a really, really good thermal conductor. So when you have thermal clearance and thermal spokes and stuff, these, like, you know, thermal reliefs or whatever, it makes it so you get like relatively strong electrical connection, but you also have, but it's also like decreasing the thermal resistance, so you can heat up that area, get the solder to melt, get the component to stick, and then like not have all of that heat just like immediately pulled away into like the surrounding ground layer. So thermal spoke must be greater than the minimum width. What's the minimum width? All right. So we are doing this, and we're just making gonna make 2 rectangles. All right, so that's gonna be for ground. Can it be on both of those? No. Okay. Haha, okay, cool. So this is that's a ground pour. Ah, yep. And it's is unable to connect these things together. So let's see if we can figure out a way to do this. This guy, then, I'm gonna move him over here. Cool, that'll work. This ground. That's unfortunate. So, something worth considering, right? So this is common cathode, right? So inside of the LED thing itself, so like inside of this thing, right? So there are 2 common cathode pins that internally they're connected together. So even though I can't get this pin here connected to any solid ground plane to connect it to the rest of it, internally it's already connected to this guy over here. So I don't have to connect it necessarily. I don't know. I'm gonna call this good enough for now. So tomorrow I'm gonna generate the Gerber files and all that sort of stuff to get it out to Fab, because it's like there's a little bit of like dotting your I's and crossing your T's that I want to make sure I do, and I'm a little too sleep deprived at the moment to make sure I do a good job with that. So I'll put a ground plane on top and then button everything up for tomorrow, and then yeah, get this board out to Fab. Wow, I'm so stoked. This is so cool. Dan, thank you for thank you for encouraging me to get shit out the door. All right, let's see if that works. Is it gonna re-pour? Come on. Please. What are you doing, Buwan? Oh, you walked into my area, so I'm gonna put you on camera. No, this is Buwan. He's a little troublemaker. But he's also a little snuggle bug. Adorable. He's a good cat. Sometimes. Cool. Very cool. That's the main copper port if I wanted to connect it to the top. Yeah, I'll do that. This thing here still needs some way, somehow, to connect. Which I might have a Easy. Okay. Just do that. Boom. Good enough. Okay. Fully connected. We can ship it. No, we can't. This here. Oh, Buwan, I gotta put you down. Need my left hand for this. Get your claws out of my shirt. Oh my goodness. I can have a trace that goes around. That's reasonable. Okay. And then, yeah. Okay, well, I'm done for the night. Yeah, so I'm gonna probably call it quits, and thank you all for my board looks beautiful. Thank you. Oh, I did not draw an outline. I don't have an outline on this thing yet. Let's do that. I'll clean it up tomorrow, but let's look at this thing. Let's see. Place a line, boop, boop, boop. Come on, boop. And then this guy, this will be on the edge cuts layer. You? No? Edge cuts. Place line. It'll be better tomorrow. Okay, cool. So there's that, and then let's check out 3D View for for posterity. 3D Viewer. Oh, look at that guy. Woo! All right. Nice. That is, man, I got half a mind to send it out like this. This is special. This is something. Woo, 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 woo. Cool. Heck yeah. Oh, thanks, Dan. Yeah, so, and like, the ground planes, like, they look good, but they feel good too. It's just, fewer traces overall. So, but you do end up with a lot more vias, as you can see. But that's okay. Those are basically free. All right. Well, everybody, thank you so much for watching. I'm gonna get some shut eye. But yeah, you guys have been great, and like I really appreciate all the comments and like getting set up with the the audio, and also just like talking about circuit things. So it's been pretty cool. So all right, thank you guys so much, and have a good night. See you next time.